Hope you've had a coffee and welcome back. Dr. Vasilius had to leave us, I think, because of the weather and the train, but we will continue the discussion anyway afterwards. First, we have our next keynote speaker, Daniel Kondermann. Daniel got his PhD in 2009 at the Heidelberg Laboratory for Image Processing. His research is around analysis, computer vision, and machine learning methods, and especially looking into the dataset architecture. It's also perfect for our workshop, where he looks at ranging from sensor array design to data annotations, and also the performance metric definition, which is also already something mentioned before. In 2013, he founded Pallas Ludens, a visual data annotation company. Joined Apple in 2016, where he was also the head of a small team working on dataset quality metrics for large-scale annotation projects. And then in 2019, founded Quality Match, where he's now also currently chief technology CEO. CEO, pardon. Chief executive. Yes. Which is a visual dataset quality assurance company, based on the hypothesis that the amount of data needed for machine learning is less important than its quality. So that's a very interesting hypothesis. I'm sure we're going to hear more about it. Short round of applause, please.
Works. Okay, so thank you very much for the introduction and invitation. Actually, I didn't do this for a while, and this is the first time I've been on a workshop for like, I don't know, 5 or 6 years, and I have all of the academia flashback, and I really like it. So today I'm going to talk about 4 topics, roughly. Probably the first 2 are the longer ones, and the last 2 are the shorter ones. I want to talk about performance analysis, which is not necessarily generating training data. It's really just trying to understand how good a method works. And that's more or less my research. That's what I did in the years from like roughly 2006 to 2012, I would say. So it's old news, so to say, and let's see how it aged. And then I will talk a little bit about dataset quality. This has always been bothering me, like what is a good data set? Like not just what is a good algorithm, what is a good data set? Because I think there's way too little research on that, way too little focus on these topics. Then I talk about dataset quality assurance, like how can we make sure that it's good? And I will focus a little bit on a smaller subset of problems. And I have 3 research questions where I would say, hey, if you do research on this field, it would be super interesting to collaborate with you on these kinds of topics, because I think they are underrepresented in academia at the moment. So we already got an introduction, so I will skip that. So I was CTO before, by the way, in Pallas Ludens, and now I'm CEO. So I changed my role, more or less on my free will. So performance evaluation. This is a very old, I copied a lot of slides actually from my old presentations and made them look similar. This one is how I started out early on. So I was a postdoc, and everyone told me, Daniel, you need to make sure that we get performance evaluation done. I've worked a lot with Bosch at that time, with the group in Hanover. And this is the concept I've been using for all of these years, I think. Like when you want to understand, when you want to make a prediction on how good an algorithm is, and how good a method is, these are all the ingredients. And what goes into this black box here is you have some data, and you don't know if you have normally you don't have ground truth or reference measurements or anything. You also need a really good problem definition, and that's something I'm gonna bring up later again. And you need to have an application in mind, because without an application, you can't have real requirements, and then the metrics don't matter, and then you have problems. So in this box, you have these 4 elements here: the reference system, the algorithms, plus the implementations. In the old time, implementations weren't available all the time. Now it's gotten much, much better. Then you need a software to evaluate stuff, and that's actually a lot of work, and that's often surprising for many people that developing this is a big deal. Like if you talk to Andreas Geiger from Kitty, he can probably sing a song about it too. And you need good performance metrics. And I did this like a long time ago. I did one IJCV paper here. Oh no, that was the NCS proceedings in 2012. That's where things started. And since then, I did a couple of 2 benchmarks and a couple of workshops I organized. 2013, I started asking myself the question, what is a good data set? This is what ended to be my company now. So if you look at reference data, let's just break it down. This is all about high concept, very little concrete research. I just show some images from papers and I will cite them. You can have reference data without ground truth. So you don't know what the right answer is or what the quality is. Then you can have weak ground truth, and I will go to that in a second. And then there's with ground truth. And for the with ground truth thing, we already have seen like simulations, for example, in the first presentation today. You can use computer graphics. They have limitations, but they have advantages, like the crash situation. I want to simulate a deadly crash. That's something that's very hard to produce in the real world and very expensive if you do it, even if it's not dangerous. So maybe you use computer graphics for that. You will always need it at some point. The other thing is you can use measurement devices. And I mean, LiDAR is also one of the measurement devices which are not just used for creating like live predictions in the car, but you can also find measurement devices to have higher resolution, higher quality, and then you spend a lot of time on that, and then you know that it's almost perfect. Problem with this is that they have measurement errors, and problem with graphics is it has realism errors. It's never, you don't have a silver bullet here. If you go to weak ground truth, one thing is that you can take more, for example, you put a lot of cameras. You say I use a light field system, for example, to record data, and they have a lot of different views. And this means I can see more. This means I can hopefully understand something or something better by using algorithms which work on this multitude of sources. And then you have more knowledge. The other approach is annotations, and that's what the industry is using at large scale still. Even though the next talk will be about the end of annotation for data sets. So this is a topic I've been working a lot on, also in my first company and now in my second company. It's the question on what errors do humans make? If I ask a human to tell me where are all the pedestrians, it can be extremely complex. It's never simple, and they make errors because humans make mistakes, and it makes it difficult. But if you don't have ground truth at all, and you cannot understand whether your algorithm works or not, you still have experts. Experts are super expensive, and they have to spend a lot of time on it. But eyeballing is a valid method of understanding whether algorithms work. So I try to make it a little clickbaity. So there are 8 truths about reference data now. And this is essentially papers my PhD students wrote, which have some sort of bottom line, which I learned over the years, and I think it's worth sharing because I think they're still valid. So first of all, computer graphics limit the realism. So this is the trade-off I was mentioning. And we actually started in 2009. That was a little bit around the time when MPI Sintel also was created for optical flow. And I had the same idea at the same moment. The difference was for MPI Sintel, the idea was let's just take what we have and produce a data set out of it. And I was more interested in how real can it get? Is it realistic enough? And that was the work with Stefan Meister, now working at Apple. We created this first set in 2009, and then it took like 1 year until we were able to actually create some realistic ground truth. Super simple stuff. We took a real object and then tried to recreate it with computer graphics in a way that it's convincing. And it turned out it's really difficult and it's really expensive. It's not like you can just say, okay, let's just render everything, because if it's in the computer, it's easy, but you need to create the content, you need to get geometry, material properties, and so on. So it's really, really complex. And I guess it's probably as expensive as creating annotated data when you look at the amount of human labor and skills you need. Second problem is when you use measurement systems, that's the other dimension. They normally don't work at scale. We try to like have these different, like we use a small statue, for example, for stereo evaluation, and created ground truth for that. Then we had this box where we just measured it with like rulers. And then we had this room where we used a LiDAR to scan it. That was my office a long time ago. And what's important for me is 2 things. First of all, you cannot run around the world and measure everything because it's going to take forever and it's going to have errors. Because here, for example, the LiDAR is very low quality. This is not a good representation. And today there's a company called Matterport, and you just put a device in and it creates beautiful 3D models. But you always have an accuracy on one hand, and the size of the objects, like the size of the space you want to measure, is also has different parameters. So it's very difficult. To creating these kind of ground truths, we had an Arrows paper here in 2012, also a long time ago. And that brings me to the next point. Measurements are uncertain. And that's something which was always upsetting and is still upsetting to me. I'm actually angry about this all the time. So if I get polemic, please excuse me for that. Very often data is generated, particularly for academia, and there is no notion of how it, rarely it's really recorded how it was created, what was the rationale, what was the accuracy, how do you know that this data is data you can rely on? And this is a huge problem, because if you train on that and then you have some ground truth and you get some, like an MAP, for example, or whatever your metric is, you have no clue whether this represents reality or whether this makes sense. The whole metric is completely useless if you don't know how good your data is. And that's something which is still being overlooked, in my opinion. But here we did it in a like, this was an ACCV paper, 2014. We really made a huge amount of effort with the University of Hanover and with Bosch here. We had this camera system where we had a stereo camera. We did a LiDAR scan, terrestrial LiDAR, so it was static. And we recorded the static scene. We had we tracked the cameras. We looked at the camera tracks. We did like a full-blown error propagation and tried to get reference data, like depth reference data with error bars. So we could, on every depth, we could say plus minus 3 centimeters, plus minus 1 centimeter, and so on. It was a huge amount of effort. It was a pain to develop, and in the end, the data set we published, like after I left university, it was taken offline. Very sad story, but that was a big learning. Always deal with uncertainty and measure uncertainty, even if it's not a measurement device. That's something what I do with my company now. Humans, you can also measure human uncertainty and ambiguity, I would call it. Humans make mistakes. That's the next one. Good next step. I was part of the Cityscapes dataset. I worked a lot with Marius at that time on the course labelings. That was my first company, Pallas Ludens. We did all of the course labelings. And here, one of the big problems was really that creating these full scene labelings is super expensive. It takes about 1 hour to create a full scene labeling of that size. And here we reduce that amount of time to 6 minutes, so by an order of magnitude. And problem is, of course, it's course, right? And you have to find ways of teaching people to do this. And for me, this was a great learning experience on both ends. Like, the one thing was, it's very hard to teach humans to make mistakes, consciously make mistakes by labeling it coarsely. And the other problem was really that we had another data set. We also did some scene labeling for Kitty back then, scene segmentation. And it's extremely hard to do the quality assurance on this kind of data, even if you annotate it multiple times. Like, what happens? You annotate this 2 or 3 times, then you have 3 versions. What do you do with them? Like, how do you know which one of them is right? You don't know. The next point, that's work from Katrin, also at Apple now. The other one was from Rahul. He's also at Apple now, all of my old colleagues at Apple. Katrin did her PhD with me on a topic of performance metrics. And I just want to bring up the topic and reference the paper here. But what I want to say with that is, depending on your application domain, you will have very different metrics. And you have to find the right level of granularity. Like, what is the depth of detail you need? Maybe you don't need this 3D point in LiDAR up to the 1-2 centimeter, but maybe you have some contextual problems, like when you use stereo, maybe you have edge fattening or edge thinning, which would mean that objects get slimmer or wider, and that could have an effect on your application, because maybe if you want to avoid objects, it's better when they are fat and worse than when they are thin. So essentially, you can come up with a whole set of metrics which are more context specific and which have more to do with your application domain. So MAP, for example, is extremely abstract to me. And I once tried to implement it. It's super hard to implement. It's not so easy. It's so easy to introduce bugs. It's really surprising. So I think for me, the point here of this one is try to have a motivation why you use this metric and try to show how it impacts the outcome you want to achieve. And really do a sensitivity analysis. When you come up with a metric, try limit cases, like what happens in this situation, what happens in this situation? Why does it matter? Why do I take these 9 metrics and not another 10th metric and stuff like that? So I think there's a lot of work. If you Google my Google Scholar profile, you will find other papers like that. And I think that's something which is still valid today, and it still makes sense, because lots of people just want to get their work done, want to get a PhD done. and then they take any metric like squared Euclidean distance, something like that, right? And then you're fine and it's good enough, and then weird results happen. So last one, oh no, there's two more. There is no best method. That's also something Katrin came up with, this radar chart idea in the same context. And I think that's super important. I was always angry about the idea, and it's still like that, that there is a best method. We always see my method is rank 1 or rank 2. Of what and why? Like if you buy a laptop, normally you have to balance like what's the screen size, what's the battery life, what's the disk size, what's the amount of memory, what's the GPU in it. What is the best laptop? Can anyone say that? No, there's no best laptop. There might be one for the use case you have, and your use case can be extremely specific. So just saying I have the best method for optical flow doesn't make sense, because maybe it needs too much energy when you put it in a car or something like that, and then it's not the best method. So I love this kind of plot because it visualizes this extremely well, and that you here, this is about stereo tools, stereo methods again. You can kind of say, okay, for example, here this green one, LPS, it has this arrow. This is one of Katrin's arrows here. Is very low compared to this one, but this method is actually better in all other domains. And when you think about that, then you can start weighting. You always have to weight at some point. You cannot reduce, like if you look at depth or optical flow, you have a lot of vectors. You have like a one-dimensional difference image of two, like a 1 million dimensional image difference. And if you take these 1 million dimensions and you reduce them to one scalar value, it can go wrong, because you have infinite options to reduce this difference between two flow fields, for example. This is infinite by definition. So this one gives you an idea on, if you first motivate your tool, your metrics, and then you put your metrics on something like that, and then you think about your application and go to the next stage, and you try to weigh them according to what you need, you get a much more refined view on what's good and what's bad. And I think it's also good for academia, because you can perform in dimensions, in certain dimensions. You can create an algorithm which is much better in this dimension and that dimension, and it doesn't hurt anyone. So I think that's, for me, this is the most emotional one for me. There's no best method. That's something I very early on, when I worked with Bosch, we created a camera system, we put it in a car, and we recorded a lot of data, and then we had terabytes of data on our system, and we had no way of understanding what data should be used for our ground truth generation. And when I was at Apple, same thing, but they had cool tools for that. I think that's an important point, and that's also something I'm working on now, on creating better tools for this. You don't just have the ground truth, you have metadata. Here it's very simple stuff like maybe weather problems, or maybe how many dynamic objects are in the scene. It was a very static data set. And then maybe here you get some heat map on I don't know what the heat map was about actually, but it's like each frame gets this heat map where you know, like, I don't know how many people are in there or something like that. And this is not so easy. And I think this is even a research problem. Like, how do you go through a data set and qualitatively explore it in order to understand what are the actual challenges in it? It's not so easy. And I think Kitty did a great job with all of their tools of having this benchmark website and having ways of looking at the data from many different angles. But I think there's still a lot of room to improve that. This one, another one from Katrin from 2016. That's approximately, yeah, that's where I started working at Apple, 2016 to 2019. After that, I didn't do publications anymore. Reference data is not training data, and this is not. This is now I'm not complaining anymore. Now it's really just a conceptual thing. What the Katrin created here is for light field evaluation. The question, like for light field, you have a camera array, and you try to understand how good is the depth map I can create from this camera array. And turns out that you can actually create these kind of test images, like in the old days when you had a Siemens star to see how good the resolution of a camera is, how the point spread function works. And if you create these, you can actually correlate that with the quality and real images. And what's so nice about these stratified scenes, about this idea that you create extremely artificial, extremely synthetic data, is that you can look at these different effects. For example, here this backgammon thing is about the resolution of the depth. So you can see it's like a Siemens star, right? The closer you go to the side, you have either a very thin or very thick structure. That's going back to this edge thinning and edge fattening idea. But you can have these for like tilted surfaces or for round surfaces to find these kind of artifacts and so on. So this is an idea, and that was also completely by her. I mean, I was a supervisor, and I now can claim it as I was on the paper, but this is actually her work. So I really like the concept and the idea that when you want to do performance evaluation, not training data, you might want to actually be super systematic about what data you create and why. And there are some very real things like this NCAP. Who of you knows the NCAP challenge? A couple of people. It's like a challenge where there are dummies, like crash test dummies, which have to be detected as pedestrians in order to not run over them. But crash test dummies look so differently that for me, it makes no sense. I really don't understand how this happened. And maybe there's some rationale I didn't see, but it sounds like a great idea to try that. So that was my research essentially. And I have to check for time, please warn me if I'm going over time. Now to the dataset quality. So there's this intuition that a poor, like you have garbage in, garbage out, right? So you have a poor data set, and now I'm thinking training again, not just performance analysis, that you say, if I have poor data set quality, you create a poor model. And there's some intuition behind this. Rather simple if you say, I have 1 million samples and they are all labeled wrong, the model cannot learn. And if I have one sample and has been labeled 1 million times and it's absolutely sure that it's correct, you cannot learn. So that's these extremes. What about the stuff in between? I always hear stories from people, but I don't see so much research on that. But that's the idea. This is also the idea now behind my company, Quality Match, where we say, hey, can we try to understand what is the quality and where does it happen and how does it impact actually the model? And if you look at this data loop, there is essentially, normally you start somewhere, I call it mission planning because it's more like for autonomous driving, but it's also valid for all other types of machine learning data loops. You try to understand what kind of data do I need to acquire in order to create a data set. Then you do record the raw data with all of your sensors. The more the merrier, as we already heard. Then often you have some automatic curation. There you have to be careful. Curation, I mean, select the data you want to annotate or select the data you want to use to create ground truth. You often have too much and you cannot look at every image. And so often you have some automatic methods. Something can be like, look at different GPS coordinates and just grid it or something like that. Others could be train a detector on finding if there are any pedestrians in there and then filter by that or something like that. There's a risk of bias, but also it makes it very fast. Then you go to the manual curation where you say, I want images or sequences which have certain characteristics which cannot be automatically found. Then you do a geometry annotation, like bounding boxes, semantic labeling, whatever, tracking, for example, key points. Then what's not happening at the moment is annotation quality assurance. It's relatively rare. Everyone does it, but most people do it by having one more person look at the image and say, yes, it's good, or no, it's bad. Also creates a lot of cognitive biases because accepting is easier than editing or repairing. And then you train the model, then you look at the model and the results, and then often you have a performance review or something that decides, should we now deploy the model or not? That's how I see this loop. And what's a little bit weird is there is this line, it's not exact, but there's more focus on the industry on how to actually acquire the data and more skills. It's really, really difficult. In automotive, you have always these fleets of cars and they produce petabytes a day and you have to somehow bring them in the cloud and store it somewhere, but you cannot store petabytes every day, even today, it's too expensive. So this is super interesting. This is also very interesting for research, I think. And then you do the annotation. That's also rarely happening, but then you do the model training. So I think academia focuses too much only on this part because I think the full loop is super interesting and there are a lot of very thrilling topics, actually interesting topics. Yeah. So what you would do in these 3 steps, that's what my company is working on, identify biases, find corner cases, that already starts in the curation. Then maybe find annotation errors, but still corner cases. And then maybe when you run a model, you understand that you ask the wrong question. You have to taxonomy problems. You say, this is a pedestrian, but actually it's not a pedestrian because it's a person on roller skates, and that makes it something slightly different. A roller skates makes it something different. And then the question is, what makes a data set good? I think it's always good to have a backronym. It makes things easier to memorize. I call it READ because it sounds nice. And then I thought about, okay, what can it be? It's three groups of metrics. So the idea here, this is it's grouping metrics. That's a trick to make a backronym work. Just group all of the metrics, so you can use any letter for that. Well, we all know representativity or diversity. That's something that's hardly really studied, and it's very hard to study as a topic because it's more like social sciences. You have a population of data, and you don't know what affects it. Like if people talk about faces, they always think about orientation and skin color, but what about haircuts? Haircuts are probably also very important. Accuracy is something which I also won't go into detail now, but of course, you know all of the different types of accuracy. It's very easy to come up with many different metrics. But don't forget uncertainty. That's a part. When you store accuracy, maybe also store uncertainty and make it difficult. And what do I mean with difficult? This data set is not difficult because you can find a decision boundary very easily. But the real world probably gives you data which you cannot make any meaningful predictions. This is what you typically say, and people say it's nice, you can find the optimal transition, and it's a bias variance dilemma, but it's super annoying. So my point here is, why don't you try to create algorithm tasks and data sets in a way that the decision boundaries are actual decision boundaries, and you can have a lot of effect on that if you really look deep into the data set, if you design a data set, or if you choose a task to actually do this. So, last topic, how do you do this kind of quality assurance? How do you make a data set read? It also works on models. And a quick disclaimer, I focus on human labeling here and classification and detection, but there are a lot of different aspects where this whole reasoning also works. Normally you have a huge effect between your product and your hardware, like you have taxonomy, you have different costs, you have different quality aspects, you have different data sources, they all influence each other. It's like setting up gastronomy. It's like so many factors that you really have to be deep in the topic to understand what you're doing. And I think you should try to be aware of as many factors as possible. Then it makes sense to differentiate between taxonomy and ontology, where you say, okay, I have pedestrians and I have animals and I have riders, but what actually makes them that? And by looking in human labeling or in quality verification, asking these things, these ontological questions, not the taxonomy classifications, you can, for example, say, this pedestrian is a human who is alive and at least 1 foot touches the ground. And if you focus on this, on the ontology level, I think both in machine learning as well as creation, as well as in quality assurance, you can leverage a lot of effects. You can then use decision trees for disambiguation. If some people are not agreeing on something, you can ask other questions. You can go through your ontology and maybe classify stuff as edge case, or you can classify stuff as ambiguous case, and that will help you a lot in the training later. You can use repeated questioning, like if I ask 5 different people, does this object have wheels? And 3 say yes and 2 say no. Maybe it's an airplane which just lifted off and retracted its landing gear. That's a typical thing you can come up with. And then you're like, oh, interesting taxonomy, because I wanted vehicles on the road, not on the air. And that's something you will learn by using repeats and by measuring its statistical power. That will enable you to create better data sets, because with these repeats, if we have ground truth, you can see that if you draw only 1 repeat from the many repeats, and then you look at the quality of the whole data set, you will see this kind of curve. This is an actual data set for ECG, for heart rates, heart rate detection. It really gets better, and this is a huge number of repeats needed for that. Like we go into saturation, you have like 20 repeats if you do the same annotation 20 times. This is a little bit of advertisement. Talk to me later if you're interested. We are building a tool which is a little bit like Tableau for visual data sets. So you can upload your data and you can look at individual annotations and individual images, and you can compare with your machine learning results, and all in a very visual manner, very easy to filter through. And I think that's something that's also still missing a little bit. There are a couple of tools, but they are not working the way I would like to. Last 3 slides. Research questions. What about this here? Like, this is traditional machine learning, which teeters out at some point, goes into saturation. Deep learning is better with more data. But I do believe that deep learning and dataset quality assurance will create this kind of curve. And at some point, there's a cost, there's a trade-off between the quantity and the quality. Same with unsupervised learning, because you still need to create a data set and you still want the decision boundaries to be sharp somehow. So you can also learn in an unsupervised way. Problem quality is its own thing. If you think about the idea of solving a machine learning task, you can first think about, is this a good task? And pedestrian detection is, I just took a couple of images from A2D2 here. These are a couple of pedestrians, which are extremely hard to see, very far away and blurry. These are a couple of pedestrians which are easier to detect. If you design the problem, maybe you don't want to detect all pedestrians. Maybe you want to detect a specific type of pedestrians. And then designing the problem in a proper way will enable you to find that better decision boundary. And that's a lot of research needed. I have no clue like what we could do here, but it's just for inspiration. And the last one here, you could put this uncertainty, like if you ask multiple people and you have a disagreement between annotators, you can use this uncertainty, or you have measurements and the measurement comes with a variance. You can use this as training data. So you don't need to do this introspection into the network. Instead, you can train the uncertainty which humans would have, and then you can still introspect into the network and ask, why did the network not find the ambiguity that humans found? And I think that's super interesting because it also enables you to create better decision boundaries, because you could, like, the system could itself create this, I'm not so certain, because we're in this variance bias dilemma region answer. And that's what you could automatically learn with this kind of approach. So that's a little bit of inspiration. And now I'm done. Thank you very much. And any questions?
Questions?
So the target of your application, thanks for the talk first, but the target of your application is autonomous driving. So of course, a better perception is always great and nice, but in the end, it counts how the vehicle drives and how it behaves. So how are you taking into account this step after the perception with your company or with the methods that you?
I think the trick is to find metrics that somehow matter or that somehow have an impact. Like if you talk to different companies, they have different approaches. And very often they somehow tie a better model performance to some requirement which comes later in the system when you plug everything together. And normally we as a service company, we discuss and we ask the right questions, and then you can decide what matters to you. Because the more you want to understand the ambiguity or the more you want to find errors, the more expensive it becomes. So what you typically would do is say, yeah, I don't care about all of the small boxes. I don't need them. And my system doesn't care about pedestrians who are 200 meters away. And then we can just ignore them. So it's normally an interaction, and it's normally a way of filtering the data or of acquiring extra data. Like if you want to know an amount of occlusion, for example, you would just say, give me all of the pedestrians which are occluded less than 80%. Otherwise, the system doesn't work anyway. So please focus your energy and your annotation time on that.
So you have some kind of feedback loop also enabled, where you not only evaluate on perception, but actually on the driving behavior or something?
No, we talk to our customers and they do it. So we just give them.
But they give you feedback.
We get feedback. We have these discussions, and we have a lot of PhDs who are informed about machine learning, but not about automated driving. And then normally this is the collaboration part where we discuss and find out. Or we don't, and some customers want to keep it secret, and then we just like, okay, you get exactly what you did. And then please tell us if it worked.
I actually had also sort of a question on this, because we are missing maybe still a bit of a language, right, to communicate between the tasks.
Yes.
And then what is important, because your spider diagrams show it's a multitask, multi-objective problem. We have metrics in our data set, but we don't really think about the tasks in that way.
Yes.
Right. So is there what do we need to get there? Do you have some ideas?
I think it's like a kind of an ablation study on the whole system. So
In a fixed way.
in a fixed way, and it needs to be some sort of procedure. If you look at the pure dataset quality assurance, you can think of this red idea, something like which is very close to ISO 9001. Like you don't just do the metrics, you also do the procedures, and you fix these procedures so that everyone sticks to them. And I think this is actually happening at the moment in autonomous driving, like in the industry, really, because everyone's asking these questions, like, how can we make sure that we don't get sued in the end if the system didn't work, right? So you want at least have best practices, and they should be documented in some way. So I think generally the idea is simple. Document the processes you're using, communicate with everyone, make sure that everyone sees that this is one way of doing it. And if something happens, you're expected to actually stuck to these best practices at that time. I think that's the only way to practically do something right now.
We might be still lacking a bit in academia in this respect. I think for the interest of time, let's give another round of applause.